Hello, everyone. My name is Tony Rippy. I work on storage systems, not monitoring, at a company called 2 Sigma, which is a hedge fund in New York. I apologize in advance because I'm going to subject you to yet another histogram talk. I've been working on a project that I'm pretty excited about, and I hope you'll find it interesting as well. Now, that hedge fund also employs lots of lawyers, and they say I need to include a disclaimer in my slides, so feel free to pause the video and read that, but we're going to move on. So this is our starting point. It's a graph from my laptop. It's looking at CPU usage. And all of us together, we've collectively probably spent years of our lives staring at graphs like this. Maybe you're trying to understand how your system behaves, or maybe you're looking for behavior that's out of the ordinary. But either way, there's a common problem here, and that there's not enough data. Like, despite the data that's being shown there, the data that you're seeing is actually altered in some way. These are cumulative metrics that are being sampled on a regular interval, and that sampling is typically things like a second or a couple of seconds, which can actually smooth over the data and hide interesting features. What you'd really like to be able to do is collect as much data as you can and get high-resolution data, but that strains not only the infrastructure, your monitoring infrastructure, but also your wallet. Depending on what services that you use, high-frequency information can get very expensive quickly. Now, this isn't a new problem, and there are solutions to that, and it's histograms. Histograms are a way of collecting high-resolution samples in the client, aggregating them, and then storing efficient summaries on the server at far less cost. It works by bin counting, so you take the range of possible values that you're observing, and you break it up into buckets. And rather than storing the raw samples, you just store the count of the number of samples that fall into each bucket. And then when collected, you can use those to display things like heat maps and bar charts like you see here. And this is way better than an individual time series. I find this far more useful. But still, there's some problems here. Histograms are collected on time intervals, and those time intervals tend to be long. They're usually a minute or 5 minutes or even up to an hour in some cases. And when you collect those long of intervals, it can actually hide useful events that happen on smaller time frequencies. So that's not great. And the reason why you store them on such longer intervals is because they're expensive. Even though histograms are orders of magnitude cheaper than storing the raw data itself, it's still very expensive when compared to just normal gauge metrics. And so you tend to spread that out as a way of saving space. Also, if you're you need even more histograms, because if what you're looking for is behavior that's out of the ordinary, then you need to scale out and look at longer time horizons and to see what looks normal. And you have to usually figure that out with either arcane knowledge of your system or pattern matching to be able to understand what looks normal and what isn't. Ideally, I would like to have a graph that looks something like this. And it's two distributions. The first one is the time period you're looking at. That's represented by the yellow. And a blue one, which is some sort of a baseline that somehow tells you what to expect of your system, what normal behavior looks like. Now, not only am I going to argue, can you make this graph, but I'm going to say that you can make this graph and save a ton of disk space while you're doing it. Now, here's where I'm going with this. I don't have a lot of time. It's only 30 minutes. So I'm going to cover 3 main points. The first one is measuring the accuracy of histograms. The second one is how to take histograms and group them by similarity. And then third, I'm going to show that you can use that grouping of histograms to create a representative histogram that you can store at far less cost. All right? Some disclaimers about this. This is a fun project I do on the side. I'm no stats guy, so I might be getting some of this wrong or incorrect in places. Please let me know. And also, this is an experimental setup. This is not a working production system yet. I would love to get it to the point where we can use it. We don't use it at 2 Sigma, but that is a goal of mine. Okay, histograms aren't the only form of aggregation that you can use. There are simple things like averages and standard deviation, and there's more complex things like the summary type in Prometheus, which is the T-digest that several people have mentioned now in this conference. And when you say histograms, that's not one thing. There's actually many different types of histograms. I'm not going to go into these. I have links in the slides, so if you want to read about them, you can always look at them later. Instead, I'm going to focus on a bigger idea, which is Aggregations are all approximations. And this is something that I don't think people think about too often. When you summarize data, something is lost along the way. And you should look at, well, how accurate are these histograms, and how do you measure that? This is the first thing I'm going to dig into. Luckily, histograms, all of the different types, work by bin counting. And bin counting has its properties that you can represent it by a unified representation of the covers called a CDF. Now, CDF stands for Cumulative Distribution Functions. And I'm obsessed with CDFs. Now, I suspect that not everybody shares my obsession, so I'm going to go into what those actually are. Most people are familiar with probability distributions, or the bell curve or the Gaussian curve that we have here. This is actually a probability density function, and what it tells you is that when you evaluate this function at a value of x, it tells you the relative likelihood that that value will be pulled from a random sample. CDFs are similar. They actually are a different view on the same data. Instead of telling you a particular value, the relative likelihood of a particular value, it tells you what's the likelihood that that value or less will be drawn from a random sample. And there's a mathematical relation between them. A CDF is actually the integral of a PDF. Now there is a special kind of CDF called an empirical distribution. This is a CDF that's built from a set of samples that you collect. And the way you do that is you count how many times you've seen a particular value, and then you do a cumulative count of all the values sorted, and then you scale that by the number of samples that you collect, and that creates a CDF. And what you see here is that it ends up looking like a step case function here, right? And if that algorithm for creating this sounds familiar, well, it's bin counting. It's the same sort of thing that you do when constructing a histogram. And in fact, you can take any histogram and create any CDF from it by using the upper bound of a bucket and the number of items in that as the count of the values. Now in reality, histograms use some sort of interpolation across the bucket. So the graph, a CDF of a histogram would look slightly different than this. I'm going to leave it as the staircase function because it's a little bit easier to kind of understand what's going on. Now, when we want to measure the accuracy of a histogram, here's what I'm going to do. I'm going to create two eCDFs. The first one is going to be from the raw data. Now, in a real system, that's too expensive to keep around. You can't just keep all the raw data available. But in an experimental setup, you can totally do this. So I'm going to create an eCDF from the raw samples that are collected. And then I'm going to create a second eCDF from the histogram itself. And to measure the accuracy of the histogram, I'm going to look at the difference between these two functions. Now, there's multiple ways you can do that. And to understand the differences, I'm going to look at the different ways that Prometheus gives you to inspect histograms. The first way is a function called histogram fraction. And what that tells you is how many of the samples come between an upper and lower bound. Now, upper and lower in this case are the units of measurement of whatever you're looking at. So if it's latency, it's going to be a unit of time. If it's, say, the donuts eaten in Portland, it's going to be a raw count. So the value you get back is called a rank. And it tells you where the data that you've selected lies relative to all the other data. You can think of it as kind of like a percentage, but it's called a rank. And luckily, this rank is independent of the data. It's on a scale of 0 to 1, no matter whether you're looking at latency or you're looking at disk usage. It's the same values. But it's important to emphasize that this is an approximation still. It's an estimate of what the actual rank is. And as you can see here, like there is a difference between the raw samples and the histogram. And this difference is called rank error. And if you look at a lot of studies around the accuracy of histograms, this is mostly what they call out. And also the Kolmogorov-Smirnov test, the KS test, is also based on rank error. The second way that you can measure error is histogram quantile in Prometheus. And in this one, you give it a percentile. So you can say something like, give me the 99th percentile latency here. And that's a parameter Q into this. And that will return you a value where roughly, how it estimates that 99% of the values are less than or equal to that value. And this also is an estimate. It's not accurate. There's going to be a difference between the 99th percentile of the underlying population and the number it gives you. And that's called value error. If anyone has read the DD sketch paper, which is another type of histogram, the thing that they're optimizing for is relative value error and trying to minimize that. Or actually put it within known bounds. All right, what I did for my experiment, though, was something different. I actually looked at the area between the two graphs. And if you think about it, it's actually a product of the value error and the rank error combined. And so I like it for that. It includes both kinds of errors. But also, I like it because it helps me pass the eyeball test here. If you minimize the difference between the two graphs, then when plotted on a dashboard, it's going to look similar and hopefully convey similar information to the user, the human who's actually staring at the dashboard. And so I thought this might be a good, useful measure of difference or error. So now that we've talked about how to measure that, I get to the second big idea, that histograms are actually a form of lossy compression. You have a whole set of data that compresses down into this compressed form of bin counts, and you're compressing these things. And anytime this is just like an image, like encoding as a JPEG, right? Some information is lost, but you can still see the image. And when you're accepting lossy compression, that means you're willing to accept some error. You have an error budget. And anytime you have a budget, you're like, how can I spend it best to get the most out of it, right? So one question I was asking myself is there any other kind of compression that we could fit into that error budget? And I would like to propose one such method, which is the clustering of histograms. Clustering, for those who aren't familiar, is a set of taking objects. Now, this is objects in the mathematical sense. It can be anything. It can be a number. It can be a color. It can be a unit of time. In this case, the objects that we care about are actually histograms. That's kind of a weird thing to wrap your head around, but bear with me for a minute. So you take these objects and you divide them up into groups. And what you try and do is you want to make sure that any of the objects in a group are as similar to each other as possible. And so how do you tell whether they're similar? Well, we just did that by measuring the accuracy of histograms. So we're going to look for ones that have the smallest difference between them and count that as similar histograms. So once you have all those pieces in place, then you actually need to group them. And there's lots of different ways to do that. I've listed some of the common ways up here. Again, feel free to look at the slides later for more info. I experimented with several different approaches with this, and I ended up using a modified version of dbScan, which is one of the simpler clustering algorithms. And I'm going to walk through how that works. So here I'm representing the histograms as dots on a 2D plane. It doesn't actually look like this. I couldn't figure out a good way to visualize histograms flying all around. But the way that the algorithm works is you pick some sort of random starting point. It doesn't really matter where you start. It ends up with roughly the same result. But you pick a starting point. And there's one parameter into the dbScan algorithm, which is epsilon. And epsilon is a measure of how far apart items in the cluster can be and still be in the same cluster. Now, this is going to be a distance in terms of the error that we're talking about, the area difference between the two graphs. And unfortunately, this depends on the data. If you're measuring things like donuts eaten, it's going to be relatively small. But if you're measuring something like bytes read from disk, this epsilon might be really big. So this is a parameter that needs to be tuned to the data. That's kind of one of the weaknesses of this approach. Anyway, so once you have this epsilon, you look for any points that are within epsilon radius of the starting point. And then you do that again. You add those to the clusters and start again and again until you run out of neighbors. There are no more points within epsilon of the available points in the cluster. And then you pick another random point and start again until all the other points have been assigned to a cluster, right? Once you have the clusters, you have to calculate something called a centroid. Now, a centroid is a really fancy math term for a midpoint, right? Where's the middle of this group? They don't call it a midpoint because typically the things that you're clustering aren't spatial. They don't map cleanly to coordinate systems. But the way that we're doing it here, you have a group of histograms. The easiest way to create a midpoint is to merge them all together. It's the histogram merge operation. You take all the bins and all the counts from the different histograms and combine it into one big combined histogram. And that ends up being roughly similar enough in nature to the rest of them to act as a centroid. Oh, and once we have those centroids, the important step here is that you use that centroid as the value for those histograms you collected. That means you only need to store the centroid. You don't need to store the individual histograms that were collected from the client. Think of this like a database schema. So before you do this clustering, you have a time series, and you store it in something like this table, where this table grows linearly with time. And the value that you store in the time series is the histogram, which can be quite large. After the clustering, you replace the histogram with a foreign key that points to a set of known clusters. And that foreign key is going to be around the same storage characteristics as a gauge metric, right? It's as cheap as a gauge. Meanwhile, you do have to store the centroid once as a histogram in this table, and it's still many bytes, but you're putting it in a table that has bounded growth. And I will get back to that, I promise. But first we need to cover one thing, which is this is a monitoring system. It's easy enough to run a clustering algorithm on one batch of data, but you have new data that's arriving all the time, so it needs to work on a stream of histograms. And the way that I do that is that you have some sort of a working set in a batch that you collect. And there's one modification to the clustering algorithm here, which is when a point comes in, you check it first against all the other known clusters. And if it's within epsilon of one of the existing centroids, you map that to that cluster immediately. Otherwise, you run the algorithm as you would. OK, now I mentioned that the growth of the clusters is bounded. And this is non-intuitive, right? But try to imagine the set of all possible behaviors of your system as a 2D plane here. All these blue circles are the clusters that you've seen, which represent observed behavior, right? And the blank space between these are behaviors that you haven't observed yet, right? When a new data point comes in, if it happens to lie within an existing cluster, then great. It's assigned to that cluster and then nothing changes. But if it lands outside the cluster, then what this means is that it will eventually become a new cluster and take up some area of epsilon around the available space. And over time, you'll get more and more that fall outside the bounds, and there'll be more and more and more clusters added. And as time goes on, it becomes more and more likely that existing data or new data that comes in will be mapped to an existing cluster. All right, enough of the theory. Let's try this in practice. I ran a series of experiments. I pulled up a bunch of public monitoring data sets that people have published in the past. And I ran through these scenarios and measured very carefully of the results. The first thing I looked at is convergence, like how quickly does it go to a bounded number of clusters. Oh, sorry. No, I should talk about the data I'm using. The first data set I looked at was Bjorn Rappenstein from Grafana Labs. And he published a bunch of data for testing of histograms from Cortex and Gesture logs. That's a collection of monitoring data. There was a lot of data here, but unfortunately it was only 2 minutes worth, which wasn't enough time to really see convergence. So I didn't use this data set, but instead, luckily he published a second data set, which was the query logs. And that gave an hour's worth of data, and so I used this as the initial data set. When I mapped how many clusters were being generated over time, I was a little disappointed with this, right? So what I did is I did multiple runs through the data with increasing amounts of epsilon, which means you're accepting more and more error as you go. And I expected to see fairly rapid convergence, but here it looks almost like straight lines, right? I promise you that it is curving. It is converging very slowly over time. And this is a little bit of a problem because if it converges too slowly, then at the end you end up with an unwieldy number of clusters, which can slow your algorithm down. But as you increase epsilon, then it does converge faster. The next thing I looked at is how many samples are mapped to clusters. And in this case, you see a big spike at the front. That means one of these clusters got a huge proportion of the samples mapped to it. This is actually great news because that would be our baseline. That's our baseline behavior of the system. And it serves as a useful purpose for that. And then everything else, there's this very long tail that you can't even see on the graph that goes all the way out. Those are the interesting behaviors that you would want to compare against the baseline. So this is actually very promising for my ideal graph I was looking at before. All right, so the next thing I wanted to look at was the most important bits, which is how accurate is this clustering and how much disk space can you save with it. right? Before I get into the results of that, I do want to talk about that measurement. Because if you take a step back, what we're doing is we have a set of raw data, and then we're using that to build a histogram. And then we're taking the histograms, and then we're combining those into clusters. Now, there's error introduced at every one of those steps. So intuitively, you think that these errors are going to compound and get worse and worse over time. But what I'm actually measuring is fidelity to the raw data, to the underlying data set. So I'm measuring the accuracy of the histograms relative to the raw data and the accuracy of the cluster to the raw data. And this is important because I had suspected that the error introduced by the histogram might actually get canceled out somewhat in the clustering. I don't know how many people have heard the term that a sum of errors is less than an error of a sum. That's what I suspected was going on here. And in fact, the results do show that. This graph is a measure of cluster accuracy as compared to the original histogram. This 1 over the 0 on the left is the original histogram and the error involved with that, across all the samples that were collected. And the orange line is the average as it goes. The units on the side, a value of 1 means that the cluster has the same error as the histogram. A value of 3 means that it has 3 times the error of the histogram. And that sounds terrible. That sounds pretty scary. But actually, this is fairly good news. Because what it shows is, first of all, even as you accept larger and larger amounts of error, the average error of the clusters are still within 1 standard deviation of the histogram itself. And that's pretty exciting. But even more exciting is as you increase the amount of error, epsilon goes up, the error grows slower. This is the canceling out of error that I was talking about. So this is sublinear growth on the error over time. Now, when you compare that to the disk savings you get by doing this, oh, what happened? Okay, when you compare this to the disk savings that you get by doing this, disk savings actually grow faster than the amount of error it grows. It's superlinear growth. And this is great because that means this is an effective lossy compression technique. You can make a reasoned trade-off of space versus accuracy with this. And at this point, I was feeling really good about this work, but I wasn't done yet. I had other data sets. The other one was fairly high number of requests per second, and I decided to look at a lower QPS data set to see how it behaved. This is one published from an online web store. It saw similar behavior in that it had sublinear growth of error over time, but the disk savings went way down. And this kind of surprised me. Like before, I was converging towards 80% disk savings, and this is just a little over 50%. What happened? And I dug into it, and I eventually figured it out. And what this is Amdahl's law. So basically, what you're doing to save this space is replacing a histogram with a foreign key, right? If that histogram were the same size as the foreign key, then you wouldn't save anything at all, right? But if the histogram is really big, you're going to save a lot. And what was actually happening here? So you can actually map out this behavior. So if you know how big the histogram is, you can calculate a theoretical limit of how much disk space you could ever save, you can possibly save. And that's what this graph represents. So the size of the histogram over, and then how much disk space that you save. And if you look at the data sets I was just looking at, the medium QPS data set, it has more requests per second, which means it's packing more samples into the histogram, and the histogram is bigger. In the low QPS data set, you're packing fewer samples into the histogram, so it's smaller, but that also reduces your potential savings. If you then go back and then put a line that shows the theoretical limit of how much you could save, what you're really seeing is that as error increases, the disk savings slowly approach the theoretical limit. I wasn't done yet. I had one more data set. That was all request logs and latency. I wanted to try it on something completely different. So I scraped procstat on my laptop for a week, and I used that as a data set of CPU utilization. And when I crunched numbers and ran a simulation on that, I saw very similar behavior. The error grows sublinearly over time, and the disk savings behaved similarly to what you did with the low QPS data set. This one is even lower because there were still fewer samples per second from the web logs. So, the interesting note about the CPU data, though, is that the clusters converged really quickly. I suspect because there's less variance in the data. Like my laptop sits idle most of the time, and so like everything gets bundled up into the things on the low end of the usage spectrum. All right. Overall, I'm pretty happy with the results. Even in the worst case, I saved like half the disk space for storing this. I was able to store a week's worth of high-resolution CPU samples in less than 2 megabytes, which I view as a win. Now, this has problems. It's not all roses. So some of these problems are endemic to histograms in general, and one of them is sampling. I mentioned that you collect them on time intervals, right? Well, those time intervals matter. Like, this is a hypothetical example. You have some sort of event, and your latency spikes and goes way up and then goes back to normal, right? And if your sampling looks like this, then you can clearly see an anomaly, right? You'll have two histograms that show normal behavior, and then one in the middle, like, oh gosh, this is an outlier. There's something weird going on here. But if instead you split it down the middle, then it's not as clear. And the histogram can actually make it harder to see whether there's a spike. So this is something you have to be careful about. And so I would advocate, since you have a good compression, to use much smaller histograms or smaller time intervals. Some of the other challenges with this is that this whole accuracy versus space trade-off probably does not make sense for business metrics, right? So if you have things like KPIs or SLOs, you should probably collect that there's some other method like the T-digests. There's also, the way I use to measure accuracy depends on having the raw data. That doesn't make any sense at all in a production system. You can't, like, the whole reason you're doing this is to avoid keeping all the raw data. So I really don't have a good way of monitoring, like, how the accuracy in a real live running system, which isn't great. And then finally, the last thing is that histograms aren't free. You're doing more processing on the client to be able to generate these histograms. And if you have an application that has a really tight CPU budget, this will cause you to use more resources. So it's worth keeping in mind. There's lots of future enhancements to work on this with. For one, I'm working right now on trying to find good ways of tuning and finding that epsilon parameter automatically from the data. I definitely want to ship a working collector that can do this on live production monitoring data, and so I don't have to work with synthetic or known data sets and be able to collect that. I was hoping to have my ideal dashboard. I have all the data, but I didn't get the dashboard together in time, but I was hoping to present that today and didn't get to it. But then finally, be able to have the dashboard support and then running queries against this data. But I would love to hear what you have to say. I have the Slack channel. Please put comments in the Slack channel. I would like to know if you find this is useful. Is this something worth pursuing? Grab me later and let's talk about it. And if anybody is interested, you can take a look at the source code. It's all up on GitHub on the project Mumble under my name. And I will be posting the slides later for all the links. Thank you very much.
That's really fascinating stuff. I love it. And, Linux on the desktop.
Linux on the desktop.
We're here. We made it, people. Who has some questions? Questions from the audience?
Question about me.
Oh, thank you.
How did you generate that kind of no world of histograms? Was it just by varying bin size or some other variable? Like, as you were showing that slide with the clustering.
Yep.
How did you generate all the histograms to start clustering?
So how did you generate all those histograms?
Very good question. So I had the data set that is in CSV form, and I just created an app that used the Prometheus libraries. And I ran through the CSV, dumped it into the Prometheus libraries to generate the histogram, and then saved that off as a protobuf, and then went from there. Does that answer the question, or were you asking something different? Okay, yes. Let's catch up later.
Yeah, right here in the middle here.
Yep.
It's some really interesting ideas there. Can you talk a little bit about what you would build on top of this? Like could you do alerting based upon deviation from the baseline, or what are your thoughts there on what you build on?
Yeah, what are your thoughts on where you go from here?
That is a very good question. I was mostly approaching this from the angle of just saving space, but this could be very useful for things like anomaly detection. I suspect that there's probably better anomaly detection techniques out there, because some of those, like I showed the big baseline that has most of the samples, and there's a long tail, but it's probably the case that some of those in the long tail are totally fine, right? They just don't happen to map to the baseline itself. So I'm not sure how useful it would be for alerting. I do think it can make an interesting dashboard for like visually seeing where there might be different behavior. Like what I was hoping to do is put up a dashboard of like a calendar or a time frame where the intensity of values, where you can see the bright spots are things that are very different from the baseline, and kind of like smaller grades of color that show you things that are closer, closer or further away from the baseline, as a way of being able to hone in for where there was odd behavior happening. So it was mostly for digging in and inspecting data, or at least that's the way I've been approaching it so far.
Awesome. All right, we're a few minutes behind, so we're going to use this break to get back on track. So we'll reconvene in here at 3:45 in the back, snacks and coffee and drinks and all that fun stuff. Another big round of applause for Tony. Thank you so much. This is great.